All right, guys. Good morning, everyone. I will start with a few examples to review what we were discussing and introducing yesterday. Just wanna announce that I posted officer. Oh no, that's for the lab. But I guess you can also join on Friday. I will be online, even though we don't have classes at 11:30 a.m. Okay. Remember, tomorrow we have a quiz. And we have a test, the first test next week on the Thursday. If you are on my lab, there is no lab next Thursday. So we have 2 more lab sessions tomorrow and Tuesday, and then we have off, sort of. Then there are a couple of videos I posted yesterday regarding resistivity and circuits. I will be going over voltmeter and ammeter right now because that's going to be useful for the second lab. All right. If you have any questions about resistivity, I will also be doing more than an example, a few revision of the concept and the equation for resistivity. And then I will do a couple of circuits for DC current, which is what we're doing yesterday in parallel and series. And then we'll do a review. The review is going to be based on the problems that you can see on the modules there for each chapter. I figured it would be a good idea because the problems might be similar to the ones in that guide in terms of the level, right? And also the web assigned, but we've done all the web assigned. So that's covered. So let's do some extra problems today as a review for electric potential and electric potential energy, all right? I'm thinking for the test, you're gonna have chapter 15, 16, and all 17. I don't think I will include anything from chapter 18, but we will start doing chapter 18 next week, which is magnetism. All right, so we will start that next week before the test, but we will have a review also in between on the Wednesday. Okay. Remember, if you have any questions.
So when is our first test, Professor? I know we have a quiz tomorrow.
The test is next Thursday, Thursday the 16th.
Okay, thank you.
Right. Also, what I do right now is just check here the attendance. Anyway, so let's talk a little bit about what I have on the board here. So let's put this in there. I have a circuit with 10 volts and 10 volts. I chose those values because it's ideal for what I want to do now. What I want to show you is what happens when you have an ammeter and a voltmeter. So the ammeter is a device that measures current. And it's always connected in series. So it's important because if you connect an ammeter in parallel, you will blow up the device, right? The fuse inside the device. The voltmeter is connected in parallel. And this is used to measure volts, of course, voltage, and it's connected in parallel. Every device that we use in electricity, a voltmeter, a power supply, a battery, and the ammeter and voltmeter, they have what we know as internal resistances. So they both have internal resistances in ohms. The internal resistance for a voltmeter, so for the voltmeter, it has a very large R. For the ammeter, however, is small. This will make a lot of sense, well, in a lab, if you were measuring this, but when you do resistances in series and parallel, you will be using devices like this, and then you will see how the current doesn't change as it's or it doesn't change as much. But we're going to prove right now, right, that there is a small change. Almost negligible, but there is. All right? Normally, we say that the resistance here is very large. So let's say that the resistance in the voltmeter is around 100 times the resistance on the value of this resistor, right? So if we were to ignore the voltmeter, the current will be 10 divided by 10, 1 ampere. That's your theoretical value for the current. However, we know that because there's a voltmeter, it's gonna split, right? But this one and this one are in parallel. So they always have the same voltage. So I can figure if the resistance here is 100 times bigger than this, then the resistance here is 1000 ohms, right? So if I know that the voltage is 10 and the resistance is little r 1000, then I know here the current on the voltmeter is 10 divided by 1000, which will be 0.01, right? I cancel a 0 and it will be 0.01 amperes. So the current on the resistance R is 1 minus that 0.99 amperes. So what's the error between 1 and 0.99? The error, so if I do here the error I detect will be the 1 minus 0.99 divided by 1, this is the theoretical value, times 100%. This gives you exactly 1%. Right? Of course, the error depends on how much bigger is that. The larger the resistance in the voltmeter, the lower the error will be. Because the lower this current will be. All right? So that's how you use voltmeters and ammeters. So hopefully this will help you for the lab. All right, for that question. And to understand basically parallel and series, right? If you were to have an ammeter, right? So there's not really a question like that in the assignment either, but in the ammeter normally, a resistance here in the ammeter can be approximately 0.01 ohms. So the error is also around 1%, right? Because what you will measure in this case is how much potential is being lost due to that. Since the ammeter is in series, right? Then you know, let's suppose there's no voltmeter. So the current is 1. So 1 times 10, 10 volts. 1 times 0.01, 0.01 volts. So you should have 10.01, but you are supposed to have 10 volts. So the error will also be 1%, right? So normally, because the ammeter has a very low resistance, the potential drop, that's how you call it. The potential drop in the ammeter is very low. So you take it as if there is nothing in there, right? That's how you use these two devices, okay? So I know you're not using them per se hands-on, but at least I hope that this helps you to understand that, right? So let's go now with resistivity. If you have any questions about this, please let me know. But again, it's an application of Ohm's law, right? Okay, so let's talk a little bit about resistivity and how it's supposed to behave in terms of Ohm's law and the equation of resistivity per se. So for resistivity, first of all, Ohm's law right? R equals to V over I, right? But you also have that resistance is resistivity length over area. So for people who are not in my last session, all right? What happens if you plot resistance versus L divided by area? That's going to give you a linear plot. Based on this equation, it's like saying Y equals to MX. So this is resistance in ohms, and this is length divided by area. If you think about it, the units are 1 over meter. So you have different points, right? And you can pass on a line, right? And the slope is the resistivity. You need to make sure that that's the units. So area has to be meters squared and resistance is in ohms. All right? Why is that? Again, from this equation, right? This is like saying Y equals to MX, where M is the slope. All right? Furthermore, if you were to plot using that now, Ohm's law, IR equals to V. So if you plot, it doesn't matter, but normally you would plot R versus I, right? The plot will give you something like this. That's because I and R are inverse proportionals, right? What does that mean? That I times R are constant if the voltage is the same, right? That's what that curve means. This means that they are direct proportional. The bigger the R, the bigger that is. Okay? And then we did some problems using the different sizes, different areas. All right? Something I wanna put here. If you were given, for example, 2 millimeters squared for the area, that you multiply by 10 to the negative 6 to make it meters squared. All right? Don't forget that 1,000 millimeters is 1 meter. Okay? That's important. SI units. All right? Okay. Now let's go and let's do a circuit problem where we have resistors in parallel and series. Let's do a couple of those and let's see if that's clear. All right, remember that if you have any questions, please let me know there. I'm always checking the chat. All right. And this should help you for the plots that you have for the resistivity lab, right? That's basically what you have to do. Okay. The units are very important, especially for area. All right. We always, because we're dealing with very small devices like cables and stuff, we measure in millimeters, centimeters, right? But everything has to be changed at the end of the day into meters, ohms, and amperes. In fact, in a lab, depending on the value of the resistances, because you're not always going to have 4, 3, 6 ohms. You have 1,000 ohms, 10,000 ohms. So we measure currents in many instances, we measure them in milliamps. So that is important that you know how to go from one to the other. So here I'm doing a circuit now. Again, I'm gonna put a resistor here in between. Like that, like that. And it's all gonna be connected to a battery here. Like that. Let's give some values that actually help. So 3 ohms and 6 ohms. Yep. 2 ohms, 4 ohms, 12 ohms. All right, so 28 volts. Let's see if I got this right. So the battery is 28 volts, and you have 2 loops now, and 1 resistor in the middle. So let's recall our theory. What we know from the theory is that the current, even though we know it should be going this way, right? Electrons flowing. The convention we are going to use is that the current goes like this. Right? That's your current of the circuit, I total. And then it's going to encounter that junction. So it's going to be divided in here and here. Right? And then you will have the current meeting at this junction here, and then again this total current will be here, right? It's split, it goes back to the same, but then it splits again, and then we have that they join back here, and then goes all the way there. In real life, in real life, it's not very common to see circuits as simple as it is. Yeah, believe it or not, that's a very simple circuit. All right. In real life, you have more loops and other devices, right? So we will get close to more realistic circuits when we go into Kirchhoff laws. One difference that we will be doing in Kirchhoff laws next week, or maybe even tomorrow actually, is the fact that we normally have more than one battery, more than one power supply, all right? So in a real scenario, if you have two or more batteries and 2 or more junctions, 2 or more loops, you have to use other rules to understand how the current behaves. So it's not as easy as says there is a junction and it splits. It's not that easy, right? There are other things going on, and there are other rules that we will be applying. But for now, we can use this, right? Okay, so the first step will be to find the equivalent resistance. So first of all, we know that this is in parallel, and this is also in parallel, and then these all 3 are in series, right? So again here, 1 over R, 1 over 3, 1 over 6. If you do your math, this will be 2 ohms. Here, 1 over R, 1 over 12, 1 over 4. So R becomes 3 ohms. So I can put here 3 ohms, 2 ohms, so 2 plus 2, 4 plus 3. The equivalent resistance is 7 ohms. So we put here 7 ohms. Part B, find the current on the circuit, the total current. Using Ohm's law, V over R equivalent. 28 divided by 7, 4 amperes. So I have half the problem, or even more than half of the problem solved, right? I found REQ, I use it to find the current on the circuit, 4 amperes. Perfect. Now, let's split the currents. We have to find the current on 4, the current on 12, the current on 2, the current on 3, and the current on 6. All right, can somebody tell me what's the current on 2 ohms? So what's the current here? Just think about it. You might go in the exam right now. What's the current on 2 ohms there?
Is it V divided by R? So is it 28, 28 divided by 2? But I think that's...
No, it's 4 amperes. Your current, if you were doing what you said, you will have 15 amperes. You can never have more current than the total current. That's the maximum current you can have in the circuit. The current here is 4 amperes. Because if you look at what I did on the graph, right? The current 4 amperes gets split, it's divided, and then it goes back to what it was originally. How much was originally? 4 amperes. So for this resistor here, it has all the current. This is the total current. All right, so very important. You can never have more than the total current on any electrical device inside the circuit. That's why it's called the total current, I total, or I of the circuit. All right, that's the maximum value. So that means that the current on 4, 12, 6, and 3, they all have to be less than 4. All right, so that's already an idea of what the answer should be. And that will help you to know if you're doing something right or wrong, okay? The same happens with capacitors. When we do review capacitors today, the charge of the circuit, the total charge, you can never have more charge than that in any capacitor, okay?
Sorry, Professor, can you tell me again how you got 4 amps for the total current on B?
Divide 28
Oh, okay.
equivalent resistance.
Okay, I was reading that as 23. I'm sorry.
All right, so 28 divided by 7, that will give you 4 amperes. All right, so how do you find the current on 12 and 4? Like we did with capacitors, I'm gonna find the voltage here. Why? Because the voltage on 12 is equal to the voltage on 4. Okay? So these two are in parallel. Let's put here parallel. Right? So they share. So is V4 equals to V12 equals to what? Equals to the current 4 times 3. It's 12 volts. So how much is 12 volts divided by 12? 1 ampere. How much is 12 volts divided by 4? 3 amperes. How much is 3 plus 1? 4 amperes. You see what I did there? I split the current using the potential drop. Right? So I found the voltage on the loop. The same here. on this loop. On this loop here, I want to find the voltage on that loop. 3 and 6, they also share the same voltage, which is 4 times 2, 8 volts. So what's the current on 3? 8 divided by 3. What's the current on 6? 8 divided by 6, 4 over 3. All right, those are fractions. 4 over 3 plus 8 over 3 is 12 over 3. How much is 12 over 3? 4 amperes. So that's how you do it. Any questions? Come on. So I want to do another circuit. This actually could be a question in the test. Not gonna lie. So I feel like resistors is actually easier than capacitors. Numbers like that, of course. All right, I normally give very nice numbers, but the level will be like that, right? REQ, the current on the circuit, and then find the current. I'm not gonna even ask, find the voltages, because that's part of the problem already. I will just ask to split the currents. In fact, for tomorrow's quiz, for capacitors, I probably will just ask to split the charge as well. All right. So, does anybody have any questions about this? Nobody? Okay. It's all recorded. Yes?
Sorry. How did you get V3 equals V6 equals 8 volts?
You multiply the total current by the resistor on the loop, which is 2. So 4 times 2, 8 volts. You know that these two combined give you 2 ohms. So you just need to multiply the total current by the 2 ohms. Make sense?
Yeah, I got it. Thanks.
It will make more sense, and that's the thing. That's why this is not going to be in tomorrow's quiz. It will make more sense when you do the lab on this, which is tomorrow. So tomorrow, is in series and parallel, and you will be doing all this. All right, and practice is the best way to master all this. So as more you practice this, as more clear things will be. Right? Let's do another circuit now. All right. Please make sure that you are also watching the videos I uploaded. All right. Because they complement all this with the videos you have. Oh, by the way, is everybody having access to the lecture videos, the lecture recordings? Or is anybody having any issues to access them? Oh, there is a question.
I haven't had any issues, Professor.
Okay, yes, it should be all embedded already in Canvas. If you need a password, all the passwords are in announcements, right? But they are already embedded. If anything was to happen with those videos, I have backups, okay? So don't worry, we won't lose any recordings. Okay, let's do another circuit. Let's do it a bit more complicated now. Or at least another type of circuit. So now we are gonna have battery here, positive, negative, a resistor here, and then you will have and then you have a split here, a junction, but You have a resistor here. There's another junction inside. Like this. And then another resistor here. And they close here. And they go all to the battery here. All right, so that one, they have here 2 ohms, 8 volts, positive, negative there. 5 ohms, 10 ohms, so we will probably get fractions in there. That's okay. 3 ohms, 4 ohms. So, okay, so we're gonna find everything as we have. First, the equivalent resistance, and then the total current on the cell. Let's understand again what's happening on the problem. We have the current going like this. Then it gets split. Like that, and like that. Is more in here, right? So it gets split and then it's split again. It goes back. That's another junction here, junction. 1 here, so there's 4. And now they go back here, all the way back in there. So this is the current total, and then we want all the equivalent resistance. All right? Okay, so let's start. The equivalent resistance is the easy part, right? Just do series and parallel. So we go from the inside to the outside. So the first thing will be to deal with this loop. All right, so for this loop here, they are in parallel, 5 and 10. 1 over R equals to 1 over 5 plus 1 over 10. So how much is the R? 10 over 3, right? 10 over 3 ohms. So I have 10 over 3 ohms in series with 4 ohms. And then all of them in parallel with this guy here, 3 ohms. All right. So all this was converted to this. Now, 10 over 3 plus 4, these are in series. If you add them together, you will get 22 over 3 ohms. If you do the series combination. And now we're gonna do parallel between this and this, right? So 1 over R equals to 3 over 22 plus 1 over 3. Now, if you want to do this quickly, the rule will be, actually no, this is fraction, right? So 66, then I have 9 plus 22, that's 1 over R. Then R will be 66 over 31, all right? At this point, you can estimate that. So let's do fractions, let's do decimals now. So 66. Okay, so this resistance of all this is 2.13 ohms. So let's use decimals now. But then I have 2 outside. So all this is 2.13 ohms. And this 2 is outside. So the equivalent resistance will be 2 plus 2.13, 4.13 ohms. So that's the value for the equivalent resistance then. All right. So again, I had this, the only thing that was harder here were the numbers, right? You had a fraction for the equivalent here, which is there. Then I had them in series. When you join them together, you get that. And then when you do the parallel between 3 and 22/3, you get this. And then with 2, you get that. And to find the current on the circuit, you just divide 8, divide by 4.13, 1.94. So the current on the circuit will be 1.94 amperes. Because this circuit is longer, or is more difficult, the only thing that you could be asked, right, once you finish this, will be find the current here and find the current on 3 and 4 amperes. So let's ask those questions. All right. Let's do that in there. So you can write it down. So as an extra, now we're going to split some of the currents. Let's find the current on 2 ohms, and then I want you to find the current on 3 ohms. On here, and there. So directly, what's the value of the current on 2 ohms?
1.94.
Yes, very good, right? It's 1.94. Just if you look at the graph, at the lines I did, the total current is the one that is passing by 2 ohms. It doesn't split. It only splits when it enters the loop. So very good. The current on 2 is 1.94 amperes. Almost done. Now, let's find the current on 3. To find the current on 3, because you're inside this loop, basically here, right? You want to find the voltage here. There are 2 ways you can do that. Let's suppose you are, or let's suppose you did it like I did here. You know that the resistance of this loop is 2.13. So then, right here, the voltage on the loop is the voltage on 2.13. And that voltage is 1.94 times 2.13. So that will be, so this will be 1.94 times 2.13. That will give me, I'm going to give you the other way as well, okay? So 2.13 times 1.94, 4.13 volts. What's the other way to know this guy? So how do you know that that's 4.13? Easy. The current here, as you said, was 1.94 amperes. by conservation of energy and charge, the total voltage of these two, the loop and this resistor, has to be 8 volts. How much is 2 times 1.94? 2 times 1.94 is 3.88. If you subtract 8 from there, you get 4.13. So you can also use 8 minus 1.94 times 2. That gives you also 4.13. So why do I need that? Because the current on free will be 4.13 divided by 3. Why? Because the voltage here is the same as the voltage here, right? So that current will be 1.38 amperes. Less than this, right? And easy, the current here will be 1.94 minus 1.38.56. I didn't ask that. So that was a bit more complicated, but the idea is the same in terms of splitting the currents, right? If you have a resistor outside of any loop, it's easy to know what's the current and also its potential drop. And you can use that to find and split the currents here. Right? Are there any questions about this? So we will be doing more of this tomorrow before we introduce Kirchhoff laws after the exam. All right? What I want to do now is, I think will be a good time to start doing a review for tomorrow's quiz. Okay? But again, make sure when you are studying this, okay, that you finish the homework now 4 and 5, which are DC circuits and resistivity and resistance, and that you take a look at the companion videos I'm gonna be uploading, all right? Plus the class recording. That should be more than enough to prepare you for the test next week. So all this material will be for the first test, okay? So let's go and do a review. If you have any questions about, so now we're gonna be doing review of chapter 16, please let me know, all right? And I decided to use this review guide, so the sample problems, because a lot of people are trying and are attempting these problems, so it would be a good idea to show you some of the solutions, okay? So let me just see how many people have sent to. Okay. All right. Okay, let's calculate, so review of chapter 16, right? So let's start with this. So this is review for chapter 16, electric potential energy. Let's start with this problem. So this is a isosceles triangle, isosceles. The charge, we're going to put 3 charges, -2 nanocoulombs, -3 nanocoulombs, +12 nanocolumns. And I'm just gonna give you the base is 10 centimeters. And this will be 13 centimeters. Find the potential at the midpoint here. So let's find the potential at P. All right? Let's suppose that you get a question like that tomorrow. The first thing you have to do is say, all right, it's a isosceles triangle. What equation do I need for the potential? B for point charges, K, Q over R in volts, where K will be given to you. K is 9 times 10 to the 9 Newton meter squared over coulomb squared. All right. So, because it's not an equilateral triangle, you don't know the angles. You don't need them anyway. In a isosceles triangle, the height goes through the median through the bisector. So this goes exactly at P, this height. So you have here a right triangle. This is 5 centimeters. 5 centimeters. What's the value of the height? How do you find the height? You use Pythagoras theorem, right? So 13 squared equals to, let's call this H squared plus 5 squared. So if you do your math, H is equal to 12 centimeters. That's the value of H. So now let's find the electric potential. The electric potential at P is a potential due to -2 plus a potential due to -3 plus a potential due to 12. Nine times 10 to the 9 minus 2 times 10 to the negative 9 divided, what's the distance between 2 and P? 5 centimeters, 0.05 meters, minus 9 times 10 to the 9, because of -3 there, right? That's why it's minus there. This divided by the same distance, 0.05 meters. With 12 will be positive, because 12 is positive. 9 times 10 to the 9, 12 times 10 to the negative 9, divided by 0.12. So all this can cancel. And then I can factor 9 out. 9, parenthesis, -2 over 0.05, -3 over 0.05, plus 12 over 0.12. Oh, not bad. Exactly. Nine minus 40 minus 60 plus 100, right? Oh, am I gonna get 0? Yeah, I get 0. Nice. So in this problem in particular, I get 0 volts, right? 40. So yeah, I get 0 volts. So this cancels, I get 0 volts. It can happen. 0 volts. Are there any questions about the math? The units is important, right? You see how I changed every unit there? The signs, you have to carry the signs, and this extra step here to find the distance, and this here. All right. So yeah, I get 0 volts, just the numbers I put. Other than that, make sure that you're using the right equation. It's a scalar, so there's no vectors, no anything. All right. Let's see if there's another one here. Yeah, this one here. Now let's use microcolumns. This right there. Another arrangement can be on the axis. You are given -2, 4, and 6 microcolumns. So -2 microcolumns, 4 microcolumns, and 6 microcolumns. And all the distances are 0.2 meters. So I have the point here, P, and this is 0.200 meters. So freeze it fix, 0.200. So the answer has to be for 3 decimals, 00 or freeze it fix. Okay, so find the potential here. How will you find the electric potential at the point on the vertical there? You will use what I did there. But now, the distances that you need are, you need this distance and that distance there. This is 90 degrees. 90 degrees, right? 0.2, 0.2, how much is the hypotenuse? Each one of them. From a special triangle, you know that's 45, 45, 0.2, 0.2. This is 0.2 root 2. And this also is 0.2 root 2. Right? So I have the distances there. And now I can use the equation for electric potential. The potential will be V due to -2 plus V due to 4 plus V due to 6 micro. Please don't forget the units. All right, microcoulombs. So this will give me K -2 times 10 to the -6 divided by the distance is 0.2 root 2 plus K 4 times 10 to the -6 divided by between 4 and the point is 0.2 actually. 0.2 plus K 6.2 root 2. Again, I can factor K and 10 to the negative 6. So 9 times 10 to the 9 times 10 to the negative 6, parenthesis, minus 2 over 0.2 root 2 plus 4 over 0.2 plus 6 over 0.2 root 2. 9,000. Look, 6 minus 2, 4 over 0.2 root 2. So 4 over 0.2 is 20. Divided on divided by root 2, 1.414. Is 14.14. So I will get 14.14 plus this will give me 20. So that will all give me 34.14 times 9,000. I get 307,000.298. Right? 298. I only need 3 sig figs, so this can be rounded to 307 kilowatts. Any questions about that? Right? So 2 examples on how to compute electric potentials for 3 different setups. There. Remember that sometimes the answer you have to give it in kilowatts, right? Because it can be huge. All right. Which one we have? Oh, okay. So let's do a capacitor one. Let's erase this for a bit. So now they tell you you have a parallel plate capacitor filled with air. So a parallel plate capacitor filled with air. Like that. And the distance between these plates is of 1 millimeter. They give you the potential between the plates. So let's say this is positive and this is negative. So the potential between the plates is 3 volts. What's the magnitude of the sigma? All right. So they're asking you for the surface charge density. We talked about that yesterday, right? How do you find the magnitude of the surface? And then they also give you E naught. So E naught is 8.85 times 10 to the negative 12 farads per meter. How will you do that question like that?
Professor, can you repeat the question?
You have the parallel plates connected to 3 volts and with a distance between the plates of 1 millimeter. They're asking you to find the sigma. What's the surface charge density? Okay. If they ask you for the surface charge density, the only equation that relates the surface charge density is this. The magnitude of the electric field, which is like this, by the way, is equal to sigma over E naught. That's the only equation. So the problem is to find the electric field. How do you find the electric field? If the voltage is free and the distance between the plates is 1 millimeter. Right? Voltage over distance inside the capacitor give you the magnitude of the electric field. What's the voltage? 3 volts. The distance is not 1. It's 1 times 10 to a negative 3 meters. So 3,000 volts per meter. I found my electric field. Now, I'm going to use it here. So 3,000 is equal to sigma over E naught, 8.85 times 10 to a negative 12. If you're doing this problem on that review guide or in that guide there, the answer will be sigma equals to 2.7 times 10 to a negative 8 coulomb per meter square. Any questions about this? Anybody? And if I was giving you the area of one of the plates, you can get a charge, right? The sigma times the area give you the charge of the plates. All right? Okay, theoretical question. If you double the potential across a capacitor, what happens with the energy? Think about it. You have 20 seconds to answer that question. If you double the potential across a capacitor, what happens with the energy stored in that capacitor? Anybody? What's the equation for the energy in a capacitor? You should have that in an equation sheet, by the way. All right? Let's use it here. The energy in a capacitor, the most common formula is 1/2 capacitance V squared. If you double the potential, this will be 1/2 C twice V squared. 2 squared, 1/2 C 4V squared. It quadruples. So if you double the electric potential, the energy inside the capacitor increases by a factor of 4.
Professor, the U stands for energy, right?
Yep. Potential electric energy. All right. Let's do a more complicated one. A proton, all right, this is a good question. A proton has an initial speed, so let's erase this. A proton has a initial speed of 2 times 10 to the 5. So you have a proton with an initial speed of 2.0 times 10 to the 5 meters per second. It's accelerated by a potential difference and it increases. So there's a delta V and makes the proton accelerate to a speed of final 4.0 times 10 to the, so it doubles. Find the potential, so find V. All right, how will you do the problem? The data is the mass of the proton, 1.67 10 to the negative 27 kilograms, and obviously the charge of the proton, like the electron, 1.60. All right, how will you do this problem? What concept do you use? What's making the energy increase? That's what you have to use. Initial energy equals to final energy. What's making the final energy be bigger than, what's making the velocity increase? The UE Q delta V. That. So 1/2 mv initial square plus Q delta V equals to 1/2 m V final square. Think about it. If the proton was at rest, we did a problem like this before. But now the proton has initial speed. You have to add this factor. Right? Well, let's put the numbers. In fact, let's be smart about it. Q delta V is equal to 1/2 m V final square minus V initial square, right? I saw some people doing this in the first quiz. So good. That's basically what you have to do. Now, 1.60 10 to the negative 19 times delta V, which is what we're looking for, equals to 1.67 negative 27 divided by 2. Okay, why I do this? Because this square is 4 times 10 to the 10. And this square is 16 times 10 to the 10. 16 minus 4, 12 times 10 to the 10. So my delta V will be that divided by that divided by that. minus 27 plus 10 minus 17. This goes as positive, so times 100, right? So here times 10 squared. So let's do the value there. That should be around 0.5. 1.67 divided by 2 divided by 1.6, 0.52. Times 100, 52 volts. There you go. Are there any questions about this? It's conservation of energy using electric potential energy. Let's do a capacitor problem now. Capacitors, this one here. So let's do now a capacitor circuit problem, and if we have time, yeah, we should. We can do another one with electric potential energy again. So a problem like this, for sure tomorrow, there's 4 problems, all right? And the dynamic will be the same as the first quiz, all right? Make sure you all log in between 8:50 and 9 a.m. All right? Okay. So capacitor circuit. There. There you are. So 1 microfarad, 5 microfarads here. So 1 micro, 5 micro, 8 and 4. And the power supply, 24 volts. Let's find the equivalent capacitance. Find the charge on the circuit, the total charge, and per se find Q in all the capacitors. Anyway, so again, just like we've been doing, but now we charge. Gets split, goes back, gets split, goes back, there, right? Now we have 2 loops, this one and this one. Parallel capacitors, please don't forget. These are capacitors, not resistors. So we join them by adding 6 microfarad, 4 and 8. They join by adding 12 microfarads. So we can write here, this whole loop is 6 micros, and this is 12 microfarads. But 12 and 6 are in series. Capacitors in series. like this. So how much is the capacitance? 4 microfarads. That happens to be your CEQ. So the CEQ is 4 micros. How much is the charge? If the equivalent capacitance is 4, the other thing that you should always write down is the equation for capacitors. Voltage equals to Q over C. That's what you should write. So C equivalent is 4. The charge will be 24 times 4, right? That will give me 96, right? 96 microcoulombs. All right? So that's the total charge on the circuit. So I did A and B, should be very easy. Now we're gonna find Q on 1, Q on 5, and then Q on 8 and Q on 4. What's the charge on 1 microfarad? Well, we know that, again, because they are in parallel, the voltage is the same. The voltage in 1 is the same as the voltage on 5. If I know that the capacitance was 6, and the total charge is 96, then Q over 6, right? 96 over 6, 16 volts. And then by potential difference, right? By potential drop, if this is 16, everything is 24, here is 8 volts. So this loop has 16 volts, this has 8 volts. I just do Q total divided by the 6, or Q total divided by 12, that gives me 8 volts. And that's easy now. To find the charge, I do 1 times 16, 16 microcoulombs, and then 5 times 16, 80 microcoulombs. 80 plus 16, 96. And then here, 8 times 8, 64 microcoulombs, 4 times 8, 32 microcoulombs. 32 plus 64, 96. And that's the end for the problem. Are there any questions about this? A and B, parts A and B should be simple enough. What you have to be careful is how to do the next part, this part here. How to divide, how to split the charge, all right? You just have to use the rule of parallel, and if they are in series, in series. Remember, the charge and the current, they both are constant across capacitors and resistors in series. And the voltage is the same for capacitors or resistors in parallel. All right? Okay, so we have time to do now an electric potential energy, all right, which can also be a question tomorrow. All right. So they can ask you like, find the energy of the system or how much work it takes to assemble a group of charges if they all started from very far. So let's suppose I have groups of charges and I want to assemble them in one shape. I want to place them in the vertices of one triangle like I want to show you. So how much work it takes to assemble charges like the ones in this shape. This is Q, same Q. Q is 8.8 nanocoulombs, and the distances are 3 centimeters, 4 centimeters. So find the work done to assemble the cubes from very far. Work is another way to express the energy, right? Why the electric potential, remember guys, the electric potential is equal to the work done to move a charge from one potential to another. So Q delta V is equal to work, which is equal to what? The change on electric energy. But what is the electric potential? For a point charge, these are point charges, is KQ over R. So we proved in the lecture last week that the energy between charges is K, Q1, Q2 over the distance between the charges. We know that. So for this problem, I have these two first, these two, but let's not forget these two. So what I need to find is the distance. This is 90 degrees. 3, 4, this distance between these two is 5 centimeters. Right? So now let's compute the energy here at this part. The energy of the system will be K, all the Q's are the same, so you can put Q squared over, first of all, 0.04, right? Plus KQ squared over 0.03 plus KQ squared over 0.05. I'm leaving it like that because I can factor KQ squared, so that will be 9 times 10 to the 9. Q squared is 8.8 nanocoulombs, so 8.8 negative 9 squared, all parentheses, 1 over 0.04 plus 1 over 0.03 plus 1 over 0.05. Let's finish it here. So you have to read a question tomorrow. Be careful what I'm asking, okay? This is asking for the energy of the system now, or the work done to assemble the system. So the energy will be, so 8.8 squared.
Professor, I have a question.
Yeah,
For the formula we have K, Q1, Q2 divided by R. So why do we do Q squared? Is it only
because this is the same Q. Q, Q, Q.
Oh, okay. And so we need all combinations of that for
You need
every.
all combinations, yes.
Okay.
That's why you have freedom. This one, and this one, right? So 696.96 times 10 to a negative 9. Parentheses, I'm gonna do all that. The first one is 25. 20, so 45 plus 33.3. So now, if I do that, 33.3 plus 45 plus 696.96. I get 54, so around 54.58 times 10 to the negative 5 joules. Actually, negative 6 because it's a thousands. So negative 6, which is approximately 5.5 times 10 to a negative 5 joules. That's the answer. So we have covered electric potential, conservation of energy, electric potential energy, and capacitors. Do you guys have any questions that you want me to go over?
Professor, for this last question, if the Q were negative, would the sign carry?
If the Q's, all of them were negative?
If one were negative.
Okay, yes, so if one was negative, let's suppose this one here, okay? So, between these two, so let's say, if this was negative, you will have this. Minus KQ squared over this, because of the minus. These two will also be minus K over 0.04. The only positive will be these two. So just by changing the sign, the energy will be much less than that. In fact, it will be negative energy. You will be doing negative work. All right? The way you can interpret this physically is like this. What do you think will take more energy? To bring positive charges together or to bring a combination of positive and negative together? Think about physically. Forget about the math. I mean, the math shows you that it will be less work, less energy required than that. So, physically speaking, does it make sense that you have less energy because you have a combination now of positive and negative?
Yeah.
Why?
Because positive and negative charges attract, so it'll be,
Yes.
they'll attract easier.
Exactly. Since positive and negative attract, then it's easier to bring them to one position. In fact, it's so easy that they actually will try to get together, right? But the positives there, they try to repel. So if you try to bring them, is like trying to bring to, when we talk about magnets, this will also make sense. A positive pole and a positive pole, it's hard, right? But if you inverse the pole, they go together. So it's like that. Any other questions, guys? Or anything you want me to go over?
Professor, after the quiz tomorrow, we finish up chapter 17, right?
Yeah, so the quiz tomorrow will again be an hour, maybe an hour and 10 minutes, we'll see, because we're gonna go over Kirchhoff laws. Now, regarding that, Kirchhoff laws this semester, because it's summer, I will introduce you and we might have a problem. I don't think there is any on the assignments. So I'm discussing with the other professors if we're gonna have them on the exams. It's a topic that we have to cover and it's a topic on the lab for sure, but it can be a little bit long, right? So we will cover that tomorrow at the end, after the exam, after the quiz, and we will continue with that on Monday. On Tuesday next week, we should start with magnetism, all right? And then on Wednesday next week, we will do a review of chapter 15, 16, and 17, all right? So that day will be a full review day, okay? Any other questions about tomorrow's quiz?
Yeah, are you giving us any bonus questions, please?
No, not tomorrow.
Oh.
Not tomorrow. I don't think the exam is gonna be hard, to be honest. There are no vectors, no angles, no, I think it's all about knowing what equation to use, all right? Other than that, it's all applicative. If you have done the homework and you have paid attention to the lecture that we've been doing, the problem that we've done in class, it should be more than easy. If you have any questions, I'm gonna be available, not for office hours, but for email questions during the afternoon today. The topics are electric potential energy, and conservation of energy, like the question with the proton, and then capacitors in series and parallel, right? Or capacitors in general, right? To find the capacitance, electric field inside, the energy of a capacitor, and then in series and parallel, all right? So exactly, basically 4 topics, right? 1 question per topic, most likely. All right, guys. So are there any other questions before we finish?
The test is next Thursday, right?
Yeah, the test will be next Thursday. And this recording will be available after 11, all right? Something I want to show you, by the way. The problems I was doing today are in modules. So here, right? So I did this problem, I did this, I talk about these problems, and I did this problem. And the proton problem also is here. All right. Other than that, the other problems are very similar. Accelerated charges or protons or electrons on potential differences, finding a potential difference, capacitors, and energy problem. All right. All right, guys. Let's finish with the recording now. I'm already updating